Isang magandang araw sa inyong lahat. Bago tayo magsimula sa pag-solve ng isang problem patungkol sa SVCC, ay tignan muna natin ang R134A refrigerant table na gagamitin natin sa problem na ito. So sabi dito, we have thermophysical properties of refrigerants, and the refrigerant name that we have is refrigerant 134A or R134A. So nakasulat dito yung kanyang chemical name, and also nakasulat din dito na itong page na ito ay para sa properties of saturated liquid and saturated vapor. So, we have our different properties over here. We have our temperature, we have our pressure, density, volume, enthalpy, entropy, and so many more. But, ang pinaka-concerned lang tayo for this particular lecture video at sa mga susunod na lecture videos na tungkol sa course na ito ay yung temperature, pressure, enthalpy, and entropy. Aside from being used for saturated liquid and saturated vapor, ginagamit din ito para sa saturated mixture. Now, if we scroll down, we have the properties of superheated vapor. So, makikita natin na segregated siya in terms of pressure and saturation temperature. At ang special dito sa table na ito ay nakasulat ang different properties ng saturated liquid at saturated vapor for these particular pressures. So, anong advantage nito? Kung makikita natin yung table kanina, it is mainly a function of convenient numbers in terms of temperature. Wala kang makikitang 0.4 megapascals dito, for example, no? Remember, this is your pressure column, and wala kang makikitang 0.4 dyan. Ang nakasulat lang 0.38761 tsaka 0.41461. So, kung gusto mo ng parameters for 0.4 megapascals at itong table na to ang gagamitin mo, you need to interpolate. But, that will take time. So, ang gagawin na lang natin ay pumunta tayo sa superheated table at hanapin yung pressure na 0.4 megapascals. And here, pwede natin kunin yung properties ng saturated liquid and vapor. Okay, so let's demonstrate the use of this table now. Okay, so mag-solve tayo ng isang problem patungkol sa SVCC. Basahin muna natin. We have a standard vapor compression system using R134A as a refrigerant, and it is used to cool a space such that the evaporator and condenser pressures are 0.2 megapascals and 1.2 megapascals. So if the refrigerant mass flow is 0.1 kilograms per second, determine the following parameters. So malinaw na ang ating evaporator pressure ay 0.2 megapascals dahil alam natin na mas mababa ang pressure sa evaporator line kesa sa condenser line. So we have 0.2 MPa over here, and we have our 1.2 MPa over here. So, alam natin na ito ang itsura ng schematic diagram ng ating SVCC. Let us draw the pH diagram using this as a basis. First, we know that at state 1, which is the outlet of the evaporator and the inlet of the compressor, the refrigerant there is saturated vapor. So, it's located somewhere here in the saturated vapor curve and intersecting the 0.2 megapascal pressure line. So we have our isentropic process from here to here. So this is going to be our state 2s, signifying that this is an isentropic curve. But unfortunately, according to our problem letter A, our compressor has an isentropic efficiency of 75%. It means na hindi isentropic yung process natin. And by virtue of the second law of thermodynamics, dapat yung delta S when we are having a certain process should be greater than or equal to 0. Hindi nga 0 dahil hindi ito isentropic process. So, we know that our state 2 is located somewhere here. So, this is now our actual process from 1 to 2. State 3, which is the outlet of your condenser, is saturated liquid. So, we know that it's on the higher pressure line and it's saturated liquid. State 3 is somewhere here. And process 2-3 is an isobaric heat rejection process. So we have from 2 to 3. Next, from 3 to 4, we have an isenthalpic throttling. So ang reflection nito ay vertically downward. So from 3 to 4, somewhere here. And we have finally our isobaric heat absorption to close the loop. Now, let's solve problem letter A. we are asked to solve for the rate of work of the compressor, basically the power input at the compressor, if the isentropic efficiency is 75%. So we know that WC dot is equal to the mass flow rate of the refrigerant times the change in enthalpy in the compressor, which means we have H2 minus H1. And let's just take note that the compressor efficiency is 75%. From here, we know that m dot is just 0.1, and unfortunately, we don't know state 2 and state 1 yet. So perhaps we might need to solve for the for these states in order to proceed with this problem. So anong alam natin sa state 1? We know na ang quality dito, x1 ay equal sa 1 dahil ito ay isang saturated vapor. At ang P1 natin according sa ating pH diagram ay 0.2 megapascals. It's just a matter of consulting your thermodynamic tables. Meron tayong saturated tables, so we have an option to actually interpolate these numbers in order to solve for H1 and S1. But, instead of doing so, punta na lang tayo sa properties of superheated vapor dahil ang ibang tables, pinapakita niya yung saturated liquid and saturated vapor values of the enthalpies and the entropies. So, we have this. Okay? So, remember that H1 is equal to the vapor enthalpy at 0.2 MPa and S1 is equal to the vapor entropy at 0.2 MPa. So, basically, the saturated vapor enthalpy and the saturated vapor entropy, which is straightforward here. H1 equals 392.71. So, bakit 392.71? Kasi ang pressure natin ay 0.2 megapascals at nakalagay dyan saturated vapor. So, this is our enthalpy and this is our entropy. Sulat lang natin, we have 392.71 kilojoules per kilograms. And ang entropy naman natin ay 1.7337 kilojoules per kilogram Kelvin. So, we already know state 1. Now, let's proceed with state 2s. So, ang strategy natin dito, punta tayo kay state 2s kasi alam natin na si S2s ay equal kay S1 because it is an isentropic process and also the pressure at 2s, according to our pH diagram, it's 1.2 megapascals. Ang strategy natin dito, isosolve natin si H2s. And then we are going to use the compressor efficiency formula in order to solve for H2. So take note that we already know this. It's a given. We also know H1. And we are about to know H2S. And finally, we are going to solve for H2. Okay, so paano natin ito isa-solve? We are going to construct an interpolation table. So we have our entropy over here and our enthalpies over here. So using our thermodynamic table, asan yan? Our pressure is 1.2 megapascals. So let's go to this table and then locate kung saan pasok si entropy no 1.7337. So it appears to me that it's somewhere between 1.7226 and 1.7571. So let's copy these values in our interpolation table. 1.7226 and 1.7571 as our entropies, and their corresponding enthalpies are as follows. Of course, the enthalpies have units of kilojoules per kilogram, samantalang ang entropy natin ay nasa kilojoules per kilograms Kelvin. So, we are looking for the corresponding enthalpy for this particular entropy. So, whatever this is, using linear interpolation is going to be H2S. So let's just use our calculator in order to solve this problem. Let's go to menu and press number 6 because that's the statistics table. So we are going to use a 2-variable table, one for entropy and one for enthalpy. So input lang natin itong mga values na to. Okay, after inputting, we can press AC. So don't worry, i-store pa rin nyo yung data. And let's input this entropy over here. We have 1.7337, which is basically, you can imagine it as your x coordinates sa column natin kanina. And since we are looking for the y coordinates, which are the enthalpies, let us press Option, go down, and then select regression. It's number 4. So again, we are looking for the y coordinates, so select number 5. Press equals, we have 430.1521. So this is gonna be the value of our H2S. Using our compressor efficiency formula, we already know H2S. It's just a matter of solving for H2. Okay, so input lang natin yung mga values. We have 0.75 equals 430.1521 minus H1, which is 392.71 divided by H2 minus H1. And we use calculator techniques. So go to menu, press 1 to go back to the original mode. We can just input this equation and use shift solve mamaya. So press alpha equals and input this fraction, 430.1521 minus 392.71 divided by H2, which I'm going to call X, minus 392.71. And then press shift solve. It will ask you for an initial number by which it will iterate with respect to. So remember, mga calculator natin gumagamit yan ng Newton-Raphson. So maganda na mas malapit sana dun sa final answer. Problema, hindi natin alam yung final answer. So let's just input a number close to 430. Sabihin natin 435. And then press equals. So this is gonna be our H2. Can we now solve our compressor power? Of course, we already know this. Okay, so let's move forward. We have WC dot equals 0.1 times 442.6328 minus 392.71. So let's input that in our calculator. It's equal to around 5 kilowatts. So we have WC dot is equal to 4.99228 kilowatts, which is basically 5 kilowatts. So this is our compressor work. Okay, we're done with letter A. Let's move forward sa letter B. So we are asked to solve for the temperature at the compressor outlet. So basically, T2. Remember, T2S is the temperature at the compressor outlet if it's isentropic. So since hindi siya isentropic, walang ideal, let's solve for the actual temperature. In order to do so, let's fully define state 2. Well, what we know about state 2 is that the enthalpy is equal to 442.6328. I'm not gonna write the units anymore kasi sinulat ko na siya kanina. We know that the pressure here is equal to 1.2 megapascals. So now, inspecting our superheated tables, we have 1.2 megapascals over here, and the enthalpy, it appears to me that it is located somewhere in between this one, 437.83 and 448.81. So let us just copy these enthalpies together with these temperatures. We have our H versus T. So our enthalpy is 442.6328. And the corresponding temperature that we will get here is basically T2. So let's use our calculator. Again, go to statistics and then input these parameters. So after this, press AC, input 442.6328, press option, and then regression. And there you go. We have around 64.37 degrees Celsius. So the temperature at the compressor outlet is equal to 64.37 degrees Celsius. Okay? So we're done with 2 problems so far. The third problem would be the refrigerating capacity in kilowatts. We know that the refrigerating capacity is equal to the mass flow rate times the change in enthalpy in the evaporator. And that is basically H1 minus H4. So sulat lang natin H1 minus H4. We know the mass flow rate, we know H1, and it's only a matter of solving for H4. We know that state 3 has a quality that is equal to 0 because it's saturated liquid, and the pressure at state 3 is equal to 1.2 megapascals. Okay, so let's consult our thermodynamic table. We have our 1.2 megapascals over here, and our saturated liquid entropy, or enthalpy rather, is 265.91. So we have H3 is equal to HF at 1.2 MPa. And also, we know that state 4, H4 rather, is going to be equal to H3 because this is an isenthalpic process. Okay? So, kapag nalolost kayo, balik kayo sa pH diagram. Kung alam niyo si H3, di ba? Ito si H3. So, same lang yan kay H4. Let's proceed. The refrigerating capacity is then going to be equal to 0.1 times 392.71 minus 265.91. Input that in your calculator. Our refrigerating capacity is 12.68 kilowatts. We're done with 3 problems, 3 more to go. Next, we solve for the quality at the evaporator inlet. Okay, so let's define state 4. Ang alam natin so far, the pressure at state 4 is equal to 0.2 MPa, and the enthalpy at state 4 is equal to 265.91 kilojoules per kilogram. We already have 2 independent parameters which are pressure and enthalpy. So how do we solve for the quality? We know that the enthalpy at a certain point, let's say at point number 4, is equal to the liquid enthalpy at that particular point plus the quality multiplied to the HFG at that particular point. But take note that this can further be rewritten as the difference between HG and HF. So, anong mga alam natin dito? We already know H4. We are looking for the quality. And actually, makukuha natin ang mga values na ito sa ating refrigerant tables. So, let us go to 0.2 megapascals in our refrigerant table. Somewhere here. And we know that saturated liquid enthalpy is 186.69. So, this is going to be 186.69 plus X4 times Hg. So, ano si Hg? Meron kang 392.71 minus 186.69. So, H4 is going to be 265.91, and we can just solve for this using our calculator. So mag-input tayo ng number between 0 and 1 because we know that the quality oscillates between those two. So we have X4 is equal to 0.3845. So this is the quality of the evaporator inlet. We solve for the rate of heat rejected at the condenser, basically the mass flow rate of the refrigerant, times the enthalpy difference at the condenser, which is basically H2 minus H3. We have letter E, and Q cond is going to be equal to m dot times H2 minus H3, which is 0.1 times 442.6328 minus H3, which is 265.91. So again, input lang natin siya sa ating calculator. We have the heat rejection rate at the condenser that is equal to 17.67 kilowatts. Finally, for letter F, we are going to solve for the COP, which is just equal to the refrigerating capacity divided by the compressor power input, is equal to 12.68. The compressor power input is equal to around 5 kilowatts. So, if that is the case, what is our COP? So our COP is going to be 2.536. Okay, so far so good. If you have any questions, you can just comment below.